This video is made by Nihar from YouTube. This video is made by Nihar from YouTube. A transformer is a passive component that transfers electrical energy from one electrical circuit to another circuit or multiple circuits. A varying current in any one coil of the transformer produces a varying magnetic flux in the transformer's core, which induces a varying electromotive force across any other coils wound around the same core. Electrical energy can be transferred between separate coils without a metallic, conductive connection between the two circuits. Faraday's law of induction, discovered in 1831, describes the induced voltage effect in any coil due to a changing magnetic flux encircled by the coil. Transformers are most commonly used for increasing low AC voltages at high current, a step-up transformer, or decreasing high AC voltages at low current, a step-down transformer, in electric power applications, and for coupling the stages of signal processing circuits. Transformers can also be used for isolation, where the voltage in equals the voltage out, with separate coils not electrically bonded to one another. Since the invention of the first constant potential transformer in 1885, transformers have become essential for the transmission, distribution, and utilization of alternating current electric power. A wide range of transformer designs is encountered in electronic and electric power applications. Transformers range in size from RF transformers less than a cubic centimeter in volume to units weighing hundreds of tons, used to interconnect the power grid. A closed-core transformers, laminated steel cores transformers, solid cores transformers, toroidal cores transformers, air core transformers. Core transformer. Core form equals core type, shell form equals shell type. Closed core transformers are constructed in core form or shell form. When windings surround the core, the transformer is core form. When windings are surrounded by the core, the transformer is shell form. 25 Shell form design may be more prevalent than core form design for distribution transformer applications due to the relative ease in stacking the core around winding coils. 25 Core form design tends to, as a general rule, be more economical and therefore more prevalent than shell form design for high voltage power transformer applications at the lower end of their voltage and power rating ranges, less than or equal to, nominally, 230 kV or 75 MVA. At higher voltage and power ratings, shell form transformers tend to be more prevalent. 25 26 27 Shell form design tends to be preferred for extra high voltage and higher MVA applications because, though more labor-intensive to manufacture, shell form transformers are characterized as having inherently better kV-to-weight ratio, better short-circuit strength characteristics, and higher immunity to transit damage. Laminated steel cores. Laminated core transformer showing edge of laminations at top of photo. Interleaved DI transformer. Laminations showing air gap and flux paths. Transformers for use at power or audio frequencies typically have cores made of high permeability silicon steel. 28 The steel has a permeability many times that of free space in the core, thus serves to greatly reduce the magnetizing current and confine the flux to a path which closely couples the windings. 29 Early transformer developers soon realized that cores constructed from solid iron resulted in prohibitive eddy current losses, and their designs mitigated this effect with cores consisting of bundles of insulated iron wires. 30 Later designs constructed the core by stacking layers of thin steel laminations, a principle that has remained in use. Each lamination is insulated from its neighbors by a thin non-conducting layer of insulation. 31 The transformer universal EMF equation can be used to calculate the core cross-sectional area for a preferred level of magnetic flux. 9 The effect of laminations is to confine eddy currents to highly elliptical paths that enclose little flux and so reduce their magnitude. Thinner laminations reduce losses. 28, but are more laborious and expensive to construct. 32 Thin laminations are generally used on high-frequency transformers, with some of very thin steel laminations able to operate up to 10 kHz. Laminating the core greatly reduces eddy current losses. One common design of laminated core is made from interleaved stacks of E-shaped steel sheets capped with I-shaped pieces, leading to its name of EI transformer. 32 Such a design tends to exhibit more losses, but is very economical to manufacture. The cut core or C-core type is made by winding a steel strip around a rectangular form and then bonding the layers together. It is then cut in two, forming two C-shapes, and the core assembled by binding the two C-halves together with a steel strap. 32 They have the advantage that the flux is always oriented parallel to the metal grains, reducing reluctance. A steel core's remainance means that it retains a static magnetic field when power is removed. When power is then reapplied, the residual field will cause a high inrush current until the effect of the remaining magnetism is reduced, usually after a few cycles of the applied AC waveform. 33 Overcurrent protection devices such as fuses must be selected to allow this harmless inrush to pass. On transformers connected to long, overhead power transmission lines, induced currents due to geomagnetic disturbances during solar storms can cause saturation of the core and operation of transformer protection devices. 34 Distribution transformers can achieve low no-load losses by using cores made with low-loss high-permeability silicon steel or amorphous, non-crystalline, metal alloy. The higher initial cost of the core material is offset over the life of the transformer by its lower losses at light load. Solid cores. Transformer powdered iron cores are used in circuits such as switch-mode power supplies that operate above mains frequencies and up to a few tens of kilohertz. These materials combine high magnetic permeability with high bulk electrical resistivity. For frequencies extending beyond the VHF band, cores made from non-conductive magnetic ceramic materials called ferrites are common. 32 Some radio frequency transformers also have movable cores, sometimes called slugs, which allow adjustment of the coupling coefficient and bandwidth of tuned radio frequency circuits. Toroidal cores. Transformer. Small toroidal core transformer. Toroidal transformers are built around a ring-shaped core, which, depending on operating frequency, is made from a long strip of silicon steel or permalloy wound into a coil, powdered iron, or ferrite. 36 A strip construction ensures that the grain boundaries are optimally aligned, improving the transformer's efficiency by reducing the core's reluctance. The closed ring shape eliminates air gaps inherent in the construction of an EI core. 9485 The cross-section of the ring is usually square or rectangular, but more expensive cores with circular cross-sections are also available. The primary and secondary coils are often wound concentrically to cover the entire surface of the core. This minimizes the length of wire needed and provides screening to minimize the core's magnetic field from generating electromagnetic interference. Toroidal transformers are more efficient than the cheaper laminated EI types for a similar power level. Other advantages compared to EI types include smaller size, about half, lower weight, about half, less mechanical hum, making them superior in audio amplifiers, lower exterior magnetic field, about 1/10, low offload losses, making them more efficient in standby circuits, single bolt mounting, and greater choice of shapes. The main disadvantages are higher cost and limited power capacity. See classification parameters below. Because of the lack of a residual gap in the magnetic path, toroidal transformers also tend to exhibit higher inrush current compared to laminated EI types. Ferrite toroidal cores are used at higher frequencies, typically between a few tens of kilohertz to hundreds of megahertz, to reduce losses, physical size, and weight of inductive components. A drawback of toroidal transformer construction is the higher labor cost of winding. This is because it is necessary to pass the entire length of a coil winding through the core aperture each time a single turn is added to the coil. As a consequence, toroidal transformers rated more than a few kV are uncommon. Relatively few toroids are offered with power ratings above 10 kV, and practically none above 25 kV. Small distribution transformers may achieve some of the benefits of a toroidal core by splitting it and forcing it open, then inserting a bobbin containing primary and secondary windings. Air core transformer. A transformer can be produced by placing the windings near each other, an arrangement termed an air core transformer. An air core transformer eliminates loss due to hysteresis in the core material. 12 The magnetizing inductance is drastically reduced by the lack of a magnetic core, resulting in large magnetizing currents and losses if used at low frequencies. Air core transformers are unsuitable for use in power distribution. 12, but are frequently employed in radio frequency applications. 38 Air cores are also used for resonant transformers such as Tesla coils, where they can achieve reasonably low loss despite the low magnetizing inductance.